Hello all. Today we'll see database design, general normal form definitions of 2NF, 3NF and BCNF. So in the last class we were discussing about uh, normal form definitions for 1NF, 2NF and 3NF. Okay. These definitions depend on the primary key, the relation. Okay, so now we are going to give a more general normal forms 2NF, 3NF. Okay, so that is we know that a relation can have multiple primary keys. We can call keys. Okay, so if we have multiple keys, how will be the normal forms, or how can we define the normal forms? That is today's lecture. Okay, so the general outline for today's lecturers, we'll discuss about general normal forms, general definition of 2NF, general definition of 3NF, and BCNF. Okay, and so general normal form definitions for multiple keys. That is, we have considered a case where we have this normal forms, but that is talking strictly about the primary keys of the relation. Now we are going for a more general kind of definitions. Okay, so previous definitions consider the primary key only, and general definitions, that is we focus on relations with multiple candidate keys. Okay, and we actually defined the primary key attribute, prime attributes and non-prime attributes in the last classes. And initially we said that a prime attribute is any attribute involved in a candidate key. Later for this mm, defining the normal forms, we redefine this prime attribute as any attribute involved in the primary key. Okay, now we modify that. That is, a prime attribute is any attribute involved in a candidate key. Okay, that is known as a prime attribute, and all other attributes are called non-prime attribute. Okay, so any attribute that is involved in a candidate key is your prime attribute. All other attributes are non-prime attributes. And this is a general definition of 2NF. Okay, so a relation schema R is in second normal form if every non-prime attribute A in R is fully functionally dependent on key of R. Okay, so there is a small difference between the definitions of the earlier 2NF, and now we have a general definition. Okay, that is in the previous case we defined this second normal form as every non-prime attribute A in R is fully functionally dependent on the primary key of R. Now we are extending that to every key of R. Okay, so you consider all candidate keys of this relation, and what we say is every non-prime attribute A in R is fully functionally dependent on every key of R. So here every key means all candidate keys. Okay, and let's have a discussion or an example here, and 2NF normalization example. So consider a relation loads, and it attributes like property ID number, which is a primary key here, and we have a county name and a lot number. They both constitute a candidate key, and we have area, price and tax rate. These three are non-prime attributes. Okay, and property number, property ID number, county name and lot number, they are the prime attributes. Area, price and tax rate are the non-prime attributes, and we have some functional dependencies in the relation also. We have FD1, that is the first functional dependency, that is from property ID number. So it is a primary key attribute of this relation. So that determines all other attributes. Okay, so prime ID, property ID number functionally determines county name. This functionally determines the lot number. It functionally determines area. It functionally determines price, and it functionally determines tax rate. Okay, and that is the first functional dependency. And the second functional dependency is from the second candidate key to all other attributes. So that is from the candidate keys county name and lot number. They together defines this property ID number, because that is a candidate key, you know. And county name and lot number determines area, county name and lot number determines price, county name and lot number determines tax rate. Okay, and the third functional dependency is FD3, that is from county name to tax rate. Okay, county name to tax rate. So here, and we have a fourth functional dependency, that is from area to price, that is area functionally determines price. So what is the problem here? So when you consider FD1, according to the definition of second normal form, it says that every non-prime attribute A in R is fully functionally dependent on every key of R. So these are the non-prime attributes: area, price, and tax rate. Okay, this can depend on all keys, that is fully functionally dependent on every key of R. Okay, so here consider area, price, tax rate. These are non-prime attribute. They depend on county name, lot number, or they depend on property ID number. Okay. Consider the third function. So in the first two functional dependencies, uh, there is no problem, because every non-prime attribute is fully functionally dependent on the primary key only. Okay, but not the primary key, the candidate keys. Okay. And the third functional dependency is from county name to tax rate. That is, this non-prime attribute tax rate uh, is dependent on county name, where county name is only uh, a prime attribute. Okay, it is not a key. It is a prime attribute only. So that is actually a violation for this 2n. So what we can do is we can convert this into, we should convert this to into NF. Uh, so for that we can use decomposition. So loads is the original relation. We can decompose that into two relations, loads 1 and loads 2, where loads 1 contains the function dependencies FD1, FD2 and FD4, because that is not going to make any problem with the definition of 2NF. Okay, so because every non-prime attribute is fully functionally dependent on this uh, or every key. Okay, here the tax rate depends on county name, which is a prime attribute. So that is a violation of this 2NF. So we make this county name and tax rate as a separate relation, and county name is made as the primary key of that particular relation. Okay, so now this non-prime attribute depends on the key of this relation. Okay, so now these two, loads 1 and loads 2, are in 2NF. So now let's move on to general definition of 3NF. So what is the general definition for 3NF? So that definition is, before that we can define a super key. A super key of relation schema R is a set of attributes S of R that contains a key of R. It is a set of attributes S of R that contains a key of R. Okay, and the general definition of 3NF says that a relation schema R is in third normal form if whenever there is a functional dependency X to A holds in R, then either X is a super key or A is a prime attribute of R. Okay, these are the two conditions. That is, if we have a functional dependency in the relation, that is X to A. Okay, then what it says is that X is a super key. Either X is a super key or A is a prime attribute. Okay, if these two conditions hold, then we can say that the particular relation schema R is in 3NF. Okay, X is a super key or A is a prime attribute. Here again the relation loads 1. There we have two function dependencies, that is from the primary keys to all other attributes. Okay, and consider FD4. And there we have a function dependency from area to price. Okay, what the third normal form says that if you have a function dependency x to a, then x is a super key, either x is a super key or a is a prime attribute. So consider all function dependencies, that is from property id to area, or from property id to price. There either x is a super key, okay, x is a super key, or what, a is a prime attribute. Okay, either x is in that case x is a super key. So relation of a 3NF. And in this case also we have county name and lot number to property. So there the two conditions are x is a super key, that is county name and lot number that form a super key, and property id is a prime attribute, or county name lot number to area, where these two uh, our super key, and this is a non-prime attribute, but if it is a super x is a super key, that is it. Okay, but when you consider FD4, that is from area to price, so x is area, price is a, and x is neither x is super key nor price is a prime attribute. Okay, that is actually violation of that 3NF condition. Okay, loads 2, we have loads 2 also. And what we can do with this, we want to convert this into a 3NF relation. For that we again make use of decomposition. We decompose loads 1 into two relations, that is loads 1A and loads 1B. And loads 1A has property ID, county name, lot number and area. Okay, so FD1 is property ID to county name. That is the original thing. Okay, there is no violation that. And problem here is with area and price. So now we consider this area and price as a separate relation and make this area as a primary key of this relation. Now, if you have a function dependency x to a, either x is a super key or a is a prime attribute. Okay, that condition is valid. And yeah, as we go along, we see that when we convert particular relations into this 3NF, we lose some functional dependencies in the relation. That is because we are converting, or we are splitting this loads 1 into two relations, and we are moving this price to the second relation. So we lose the functional dependency with property id number to price, or county name and lot number to price. Okay, that function dependency will be lost, but still we have a relation which is in third normal form. Okay, that is the normalization example we saw is with the loads relation, and that was in 1NF, and by default that is in 1NF. And we decomposed this loads 1 into, loads 2, loads 1 and loads 2, and these two relations are in 2NF, and this loads 1 violates 3NF property, so we again decompose that into loads 1A, loads 1B and loads 2, and now that is in 3NF. Okay, and let's try to interpret the general definition of third normal form. So we know there are two conditions in the definition of 3NF. A relation schema R is in third normal form if whenever a function dependency x to a holds in R, then either a is a super key of R or A is a prime attribute of R. These are the two conditions. Okay, so we can say that condition A catches two types of violations. So we have condition A that catches two types of violations. The first one is that where a prime attribute functionally determines a non-prime attribute. Okay, so here a prime attribute functionally determines a non-prime attribute. Okay, because we have X as a super key and A as a prime attribute. It says that it catches two types of violations. That is, it catches 2NF violations due to non-full function dependencies. Okay, so there, non-full function dependency. When we have a non-full function dependency, fictional dependency, where only um, some or some keys in the or some attributes in the candidate key determine some non-prime attribute. Okay, determine some other attribute. Okay, a full function dependency is that the primary key, all the attributes in the primary key should functionally determine the second attribute or all other attributes. That is a non-full function dependency. I mean partial dependency. Okay, that is actually a 2NF violation. And 2NF says that there should be full function dependency. Okay, and we are talking of X is a super key of R. X is a super key means that contains all the elements in the candidate keys. Okay, all the attributes in the candidate keys. So that actually makes sure that we do not have any partial dependencies. Okay, because all the attributes in the um, keys of this relation form your X. Okay, that violates the or that actually makes sure that you do not have any partial dependencies. Okay, because this X is a super key of R. Partial dependency means only part of this is functional determines some other attributes. Okay, or non-prime attribute. That condition is not there because the first type of violation is where a prime attribute functionally determines a non-prime attribute. Prime attribute functionally determines non-prime attribute. That case is not there because we have X as a super key. Super key means all the attributes will be there. So it avoids partial dependency, existence of partial dependency. And the second thing is that where a non-prime attribute functionally determines a non-prime attribute. Okay, that catches 3NF violations due to transitive dependency. We cannot have a non-prime attribute functionally determines a non-prime attribute. Here we have a super key and we have a prime attribute. And because third normal forms talks about transitive dependency, there we have X to A, then A to B. Okay, so here A is a prime attribute. Either A is a prime attribute or X is a super key. So we can avoid the case of function dependency between a non-prime two non-prime attributes. So we have X to A and from A to B. Okay, that avoids the existence of this kind of violations due to transitive dependency. And we can have an alternative definition of 3NF also. A relation schema R is in third normal form, that is 3NF, if every non-prime attribute in R meets both of these conditions. That is, it is fully functionally dependent on every key of R and it is non-transitively dependent on every key of R. Okay, so that is a relation schema R is in third normal form if non-prime attribute, every non-prime attribute in R is fully functionally dependent on uh, every key of R, or that is non-transitively dependent on every key of R. That is an alternative definition for this 3NF. And now we'll see the next normal form, that is BCNF. Okay, so we have studied 1NF, 2NF and 3NF. There are also in the first class itself, we said that these are proposed by court. Now, boys also joined with this court and formed another um, normal form, that is boys code normal form, or BCNF. So a relation schema R is in boys code normal form if whenever functional dependency x2a holds in R, then X is a super key of R. Okay, that is in 3NF we have, if we have a functional dependency like x2a, either X is a super key or A is a prime attribute. Okay, so here what it says is that X is a super key of R. Okay, there is no other option. X is a super cube. If we have a function dependency like x to a, then X is a super cube. So each normal form, and which means it is something more stronger than the 3NF. Okay, because in 3NF we have either X is a super key or A is a prime attribute. That condition is not here. So it is, we consider the strictness of this normal form. This BCNF is stronger than 3NF. Okay, so each normal form is strictly stronger than the previous one, and we know that each normal form is strictly stronger than its previous form. That is, every 2NF is relation is in 1NF, then every 3NF is in 2NF, every BCNF is in 3NF. Okay, and there exist relations that are in 3NF but not in BCNF. That case is possible because BCNF is more stronger than 3NF, and hence BCNF is considered a stronger form of 3NF. The goal is to have each relation in BCNF or in 3NF. Okay, our goal is to have each relation in BCNF or 3NF. And this is BCNF example. So again consider loads 1A. There we have two function dependencies, three function dependencies. That is property ID number to county name, loads number and area. Then county name, loads number to area and property ID number. And one more function dependency is there, that is area determines county name. Okay, so BCNF says that suppose we have a function dependency x to a, then X should be a super key. Okay, so here from property to county name, load number and area, where property ID number is a super key. Then county name, load number to area and property ID number, where county name and a load number, they form a super key. Okay, but here from area to county name, area is not a super key. That is violation of the BCNF. Okay, so that is decomposed into according to BCNF normalization. This one is decomposed into loads 1 AX, loads 1 AY. Okay, and here it has only property ID number, area and load number, and loads 1AY will have area and county name. Okay, area and county name. Now area is a primary key attribute. Here property ID number is a primary key attribute. So property ID number determines area and load number. Here area determines county name. So suppose we have a function dependency x to a, X is a super key. In these two relations we can say that X is a super key. So this is a general form. Suppose we have a relation with attributes A, B and C, where A and B are the primary keys. Okay, so A, B, then we have C. So we have functional dependency. The first functional dependency is A, B to C, and the second one is from C to B. So here the second one is not a functional or that is not in BCNF. Okay, because that violates this principle. And consider another example. So we have a relation teach there we have three attributes: student, course, and instructor. Okay, student, course, and instructor, and we have populated this uh, relation, okay, with some. And suppose we define functional dependencies like student comma course, that is to instructor, and from instructor to course. Okay, suppose we have instructor to course, what will happen? Instructor to course. Suppose these two are the primary keys, student and course. To instructor, no problem. But instructor to course is actually violation from this BCNF. Okay, so how we can convert this into BCNF? We can decompose this into two relations. For example, we have R1 and R2. In R1 we have student comma instructor, and R2 we have student comma course. Or we can have R1 course comma instructor and R2 course comma student. And R1 is instructor comma course and R2 is instructor comma student. Okay, these are different ways of decomposing this relation into a relation in BCNF. Okay, so we have student to student comma instructor, and some attribute will be set as the primary key. Okay, so when we decompose this into these three forms, we can use any one of these three. So the main problem is that we have preserved this instructor to course dependency in the uh, resultant relations, but we have a function dependency student comma course to instructor. Okay, student comma course to instructor, but that is not there in any of the results. Okay, so we have lost one function dependency, that is student comma course to instructor, that is not there. So in some cases, we lose some functional dependency. But according to the principle of the database design, we know that the most desirable properties are that we should always preserve this functional dependency. We can modify these tables or relations, but we should always preserve this functional dependency, and we should always have this join property also. Okay, lossless join property. These are two conditions to be held, and we should strictly follow these conditions. Okay, but in this case, when we construct or converted this into something in BCNF, we have lost one functional dependency. Okay, so that is about this general definitions of all the 2NF, 3NF, and BCNF. Okay.